let's quickly look at the impacts again in terms of hydrocarbon storage capacity. I think I've hinted on that a number of times, but what I need to think of here is volumes. If that rock was originally, let's say it originally had a 40% net to gross, 40% porosity, sorry. Again, porosity here refers to the volume of pore space or available opening that rock has that is capable of holding oil and gas, okay? So think of it as how much of fluid can that reservoir rock hold. In this case, we're talking about volumes, okay? And then also think of it in terms of if I'm an engineer, I want to plan a well, I have a field and I want to develop it. Where do I place the well? I want to place it where I have the best reservoir rock, okay, where I have the best connectivity, where I have the best porosity and permeability, of course, right? And then you also want to also ask yourself, how compartmentalized is this reservoir rock? That will determine, okay, how much will my well produce before it dies off? How many wells do I need to optimally develop this asset or this field? So that's where this is going, okay? So you have to think of it in that regard. So let's go on. Okay, so before we look at some more, let's just think about the reservoir rock and its capacity to hold fluid. What drives those pore spaces? What controls the movement of fluid within it? First of all, there's gravity. That's number one. So naturally, the heavier fluid will go down, the lighter one will stay shallower. Think of it as gas on top of oil and oil on top of water. Okay, so gravity is there. Then there's something we also call capillary force that also drives the placement of these fluids. And then capillary force in this case is depending on what we call wettability. Wettability is just a function of, it refers to the capacity or the tendency of or the affinity of the rock, the fluid itself, for the host rock. If we're talking about oil as fluid, what is the affinity of that oil to get attached to the host rock or the parent grain, which you are seeing here? Okay, there's something we call the angle that the fluid makes. Let me just quickly sketch it if you can see that. If we have, let's say, a rock like this, I'm trying to sketch, I hope that shows. Okay, I don't think it's showing. Let me just exit the pointer. Okay, well, I'm trying to sketch, but it's not, okay, it can work now. All right, so if we have a rock like this, the host rock, and we have a fluid A is doing this, we have another scenario where the second fluid is doing that with the surface. In this very case A, this fluid makes an angle of less than 90 degrees with the surface rock, okay? In the other case, the angle is greater than, this is the angle, is greater than, it's between 90 to 180 degrees, okay? So in a case like this, in case A, we said that this fluid is a wetting fluid because it's making an angle of less than 90 with the surface. In other words, the fluid has an affinity to get through the surface, to be attached to the surface. Think of it as cohesion and adhesion forces, the interplay between the two of them, okay? In the other scenario, this fluid is a non-wetting fluid. In other words, it does not have a potential to be attached or to be absorbed by the base parent, which is the base rock, okay? So capillary force is another set of force that determines how fluids move within rocks or within the host reservoir. And then the third one is viscous force. So this is basically, depending on pressure, where you have a fluid that is between two zones that are different pressures, okay? So there's a tendency to move preferentially in one direction as a result of higher pressure. So that's basically what this is. So let's think of it as part of what we need to understand in terms of the reservoir rock and its capacity to hold hydrocarbon. In this context, I'm saying the fluid behavior is dependent on the kind of force or the dominant force that is determining how it moves from one part of the reservoir to the other. And then as subsurface scientists, there's something else we also do in characterizing reservoirs. We think about everything. I had told you, again, the external features like what is the thickness, what is the shape of the reservoir rock, where did it come from, how rapidly changing are the boundaries, okay? And then the internal features, what are the faults, How many compartments do I have in this reservoir? Do I have layering or stratification? How continuous and connected are they? We think of this as reservoir engineers or geologists, okay, as subsurface scientists. So in a reservoir characterization, you think about all these elements. The habitat also, what's the pressure, what's the stress regime in that environment, because that is also going to affect what becomes of the reservoir even after it's been altered, okay? And then what's the behavior of the fluid? You know, the type of the fluid. Is it a high API oil? What's the composition? Where did it come from? Are they fluid contacts? What are the properties in terms of viscosity and others? And then the rock themselves at the microscope, porosity, permeability, what is it? What are they? Okay, so these are things that we look at in this integrated evaluation of the reservoir